Uh-oh, it's reverted.
Let me see if I can do anything. Video setting. How about now?
Okay, now good.
Good.
Great, thank you. All right, guys. So the purpose for this tutorial is to go over the solutions for homework number 1, in hope that this will help you better prepare for the exam. Okay. We will try to go over these homework problems one by one. Okay. So for the first one, the first homework problem is problem 3-3A on the textbook. We have a list of this formulas that grows at various rate, and our task is to just what's going on? Okay, never mind. Our task is to order them by their speed of growth. And here is this is the answer key for this particular question. All right. Here is the answer for the first one, which unfortunately I don't have like individual proofs for every single one of them, but I just want to make a few notes about some of the more important classes that you may see a lot of time. Okay. So we have some of the most, let's say this. We have log n is one of the slower functions out there, and then okay, good. Okay, all right. We should do something like this. Okay, we have things like constant. Or one constant is the slowest. It doesn't grow at all. Okay. We have the next, and then we have something like log n, which is a logarithm, which is like also very, very slow. But between these two, we have a few other interesting entries, such as log n. Log n is smaller than log n, but it's faster than constant. Most likely, the next one you are going to see is like a square, or like n cube for any polynomials. Okay, so n k for some k, so k is, say, let's say 2k. 2 smaller than equal to k. Yeah, k is bigger than greater than equal to 3. And then the next one that you are likely going to see are exponential. Okay. Exponential, and then the next are factorials. Okay. And then on this question right here, we are looking at you have something like 2 to the 2 to the n, which is faster than the factorial, and we also have anything plus one step. The next step kind of is like filling the blanks and fit whichever things that goes into the in between these classes. So I should just take this into or with that. Now, I just want to make a few examples, okay? Because hopefully I don't have to go through every one of them. You have log n right here, and something that's smaller than log n is the square root of it. This one is like goes before log n, but goes faster than the polynomial, than the constant. Do you have any questions you want to ask about problem number 1? Because I feel like if I just identify these few classes or functions, then a lot of other stuffs are pretty much just
Well, I guess if there's just really any trick to it, like just to quickly see some things when I was going through it, I was like, this seems like it will be smaller, but if I try and feed in like just an arbitrary number in there, it seems like it might be bigger than the other, you know what I mean? But eventually at a certain point, there's those types of functions that if it's below this number, this is faster, but if it's above it, it's actually slower.
Yeah. That's the kind of thing that you have to pretty much just try yourself. And computers, it should be fairly simple to like write a little program and see the results. So this kind of stuff is I don't think there is really a lot of tricks into it.
Okay.
It's mainly about identifying these few classes of functions. So we have constant, we have log, we have this polynomial. Oh, and by the way, something you will likely see some that's like you have n log, right? We have seen this in class a couple times. So the key, like the stuff that goes with it is I can kind of group them into the same class because you just need to remember one thing, that log n, right? Log n is smaller than n, right? Okay, I forgot one thing right here. This here you can also be 1. K is greater than or equal to 1. So in that case, when k is 1, this n to the power of k is just linear, right? And linear is faster than logs. And we have something like say n a log n and n a plus 1. So this one is smaller than this one, because in this case we can isolate the n to the power of a here, because this one right here is really just n to the power of a times n, right? And there is this relation right here, and that kind of just helps you with the identifying the speed of growth here. Okay. And there are a lot of these complex composite functions that are in between these classes, and many of them have this kind of explanations, justifications that are provided right down there. I suggest you, if you are interested, to go over it. We are probably not gonna do this every single one of them, because it's gonna be way too much time. And I hope this should be enough for question number 1. Question number 2.
I guess it's one question.
Yes.
I guess like one that doesn't make it is e to the n is bigger than n times 2 to the n. I don't like that one has the justification.
Okay.
I wonder maybe we could go through that.
Yeah, right.
'Cause I guess I don't my logic at least is like e is like 2.7.
Okay. Yeah.
So it seems like multiplying it by n would be
Yeah,
harder than that.
yeah, that's fine. So, I wrote this down as like a class of functions where we have like 2 to the n or e to the n or something like that. It looks like this question, it does not really consider the, how should I say, wait, never mind, it does. So I should go over this. What is e to the n? All right, like you said, e is roughly 2.7, something like that.
Yeah.
Yeah, I'll just put 2.7. All right, I forgot. I don't know what the other. Okay. How about e divided by 2? That's just roughly 1.35, give or take. Okay. All right, this is a very crude way of proving that part, the question that you asked. So we have e to the n. You can write that down as 2 times 2 to the 2 times 1.35. Okay, roughly 1.35 times 2, because that is just e, right? And then we put it in right here. Right. And you remember that, let's say a e to the power of n equals a to the power of n times b to the power of n. Is that right? Yeah. Okay. So that will just leave you with, say, roughly 1.35 or something, or at this point we don't need to go over to stick with the numbers too much. So we can do something like e to 2, e over 2 to the power of n times 2 to the power of n. Do you agree with this? And so we have this as well as n times 2 to the power of n. Okay, so that's the, we can break down. That's 1, 2, 3, 4, 5, 6, 5 and 6. The function 5 and 6 in your question. So we are looking at the relationship between these two. Okay. At this point we can just isolate the times 2 to the power of n. We can like get rid of it, pretend you get rid of it. And then here we have a linear n, and here we have e to the e over 2 to the n, which, by the way, like I said, this one is greater than 1. Okay. So can we agree that this is greater than n?
Yeah, that makes sense.
Okay, does that solve the problem?
Yeah.
Okay.
Thank you.
Do you have any problem you want to ask about question number 1? We are still going on. Okay. So question number 1 is just kind of a bit of line work, especially related to those detailed cases. But for the general case, we have these few classes of functions that I want you guys to feel very good about, that when you see this on the exam, you should be able to identify it. Okay. Okay, now we go over to question number 2. Or should we spend more time on question number 1?
Move on.
Okay,
Yeah.
go over to question number 2. Question number 2, we have recurrence relations. For the recurrence relations, that's kind of a headache, to be honest. But did the professor tell you something about the master theorem when it comes to recurrence relations?
I can't remember.
Please every time we shut people down to get some answers.
Okay, let's see. The master theorem is a type of for recurrence relations of the following type: T of n equals A times over B plus theta to the power of k. This is the form of the first two questions. First two questions of question number 2. And so it says that if A equals log base B A, then Tn really is just big O of n to the power of k log n. A is smaller than that, then we have T to the power of n is O of n times log B over A. Larger than that, it's really just O of n to the power of k. This is the master's theorem, and if you want to, you can apply the master theorem to part A and B of question number 2, or if it like the problem says that you can use direct expansion, but I haven't actually worked out the direct expansion for part A or B.
I can do that.
You can do that.
Yeah.
If you can do that, that would be really nice. But
Uh,
if you want to like take a picture or something, feel free. Yeah. Which question are you referring to?
It's the same one. I think he's trying, the solution here is also explaining both.
Sure.
With defining S of n.
Mhm.
And then dividing the entirety.
Yeah.
Given over, dividing the thing.
Yeah, we can try go over it. So the thing is to divide both sides by n. That means t to the n divided by n equals so when you see that, like this one is n divided by n is really just 1 over square root of n. Okay. So that gives us t to the t of square root of n divided by n square root of n plus 1 and divided by 1. Okay. And that S equals T of n divided by n. So that gives us S of this is T of square root of n divided by square root of n. So by looking at this part and this part as well as this part, it gives us the this gives us that this equals that. And this one equals that. So what that gives us is a recurrence relation in terms of S, which is equals S of square root of n plus 1. Okay, up to now, are we good? The next step is, let's see, expand this. Let's say we can try expand this once, okay? Sn is this one for now. And then that equals S of square root of n square root of n plus plus 1, which is S of say n to the plus 2. And if we continue this trend, which is, for the record, is much easier than part A or B, if you ask me, that gives us S equals, if you expand this K times, that gives us S of, let's see, where is it? N to the plus 8, right? Okay. And the goal and the point is that this thing right here is going to become a constant. When K is we have the K right here, which is a variable, whereas this thing becomes a constant. This is the final answer. Oh, log it. I don't know if I made this clear. If you have more questions, you may ask about this one.
Yeah. All right, so, sorry, so I have to go back to the beginning here. So why are we trying to divide there? Yeah. What's the,
So this is called substitution, right?
Yeah.
If we look at the original one, we have this square root here as well as a square root inside, and apparently it's going to be very messy if you try to directly expand it. But if we do this, if we divide it by n and then come up with a s, and then use with this a little bit of workaround, we can use s to, we can express t of n in terms of s, and this s is much cleaner, right? There's no square root outside, only one square root inside, and then here there's a constant. So and we can expand this one. This one is much easier to expand than that one. That's the whole point of substitution. Oh, yeah. Forgot one thing. This is Sn. And the original Tn, because that's what we want, right? This one is right here. Tn, S is T of n divided by n. So when we have S of n right here, we want to get T, we just multiply the n back into it. So that gives us O of n log n. That's the final answer for question 2.c.
Could you also explain again the, right there, that the like almost final step there, yeah,
This one?
yeah, where you make k equal log n. That
Oh,
I
okay.
guess I'm a little lost.
Sure.
on that.
So we want to, again, like, when we are expanding we remember the direct expansion where we want to have, let's say, T of n equals something related to k and then something where, like for this case, we have, when we expand this k times, this means that we expand this recurrence relation by the number of k times, okay? And that gives us S of n in this one here. This is what we want, okay? The next step is to get rid of the S. We want to find the suitable value of k, find k such that S is found. Like where when we say S is gone, we were usually looking for a base case of some sort, where like in recurrence there is always a base case, right? Like we have k equal like n equals 1, n equals 0, or something like that. In that case, we just want to find k such that right here, here's it. We have n to this one is some small constant. That is like given an n and you square root it, and then keep square rooting it until it becomes some small number where like it's 1, like 2 or something like that. So the question is to find k. And do you want me to go over like find exactly the k here?
I guess so, yeah, I still can't, I mean, I don't know, I just couldn't, I wouldn't have thought of that at all, so that's why I'm kind of still lost.
Yeah, right. Let me see. Let's see, say, we have a small constant, let's say 2. Because 2 is easy to work with, and 2 we can do something like 2 to the power of something, and then we can get what, right? So we have n to the power, so let's say 2 to the power of x equals n, and then x equals log 2n, right? Okay, now we want to and the next step is n to the c. And to the negative. This is some logarithmic things that how do we get from n to 2, right? That's the question. So we can do n to the, I want to say 1 over x. Is that 2? Am I right? Or did I get something wrong? Is this correct? Wait, I have to think about this. This is some logarithmic algebra that been a while, and then I can forget about it. So x. Yeah. Right, that's right. That's it. Okay. Are you okay? Are we okay with this one? Since 2 to the power of x is n to the power of 1 over x is 2. Are we all good on this? Because if we can do this, then the next step naturally is to express 1 over x in terms of two. Okay, right? So k should just equals log x. And then the next step is to just that equals to remember what x is. X is log of 2n, right? So so this is that, right? Okay, go down this.
Basically, you have to take the log 2 times because the k is in like the
Yes, yes.
exponent of the exponent.
Yes.
That's the question. All right, yeah, thanks.
Okay. Are we clear on C? 2C? I mean, we have time, but the time is ticking. It's 4 already. I want to maybe speed up, or if you have questions like one particular question you want to ask now, we can probably do that and then see.
Yeah, I mean, my biggest question with C is. So like this whole dividing by n business like makes sense in hindsight,
Yeah,
like knowing the answer it makes sense.
yeah, yeah.
But how do I like approaching the problem? How do I know to do that?
Mm.
And I don't know if that's just you have to do a lot of these types of problems and it'll.
I believe this is the only, this, you can only do it by practice and like trial and error. I don't really have a good idea as it comes to like how to like magically comes up with this key number right here and how to use that. I would say maybe like go over more of the exercises on the book and see if that gives you some inspirations as to it. You have access to the answer key to the textbook as well, so you can try that. Although I should say the answer key is in 3rd edition. Right here it says this is the book, Introduction to Algorithms, 3rd edition. I don't know which version you have access to, but there is a 4th edition right out there. I believe they are all available as PDF online, but you can, if you know where to look for it, you can get it rather easily. But just to keep in mind that there might be differences. So
Right, yeah. I found it.
No. Okay, now I could go over question 2, part D and E rather like quickly if that's what you want.
Or meanwhile, I can go over A and B very quick.
Sure.
And you see, when I didn't practice it, so I might.
Okay, so the thing is, part A and B we are just going to use the direct expansion, which could be messy if you don't.
Yeah.
If you don't know what to do.
No. So this is to A. So I am here expanded for one time, then I will get. Can I get the black one? Thank you. I will get the this one. So that will be 9 square. That makes sense. I just expand it for one time. If we want to expand it for one more time, then we will get something like T and over to cube. Oh, that's fine. I will get 9 cube. where u square u minus or 3 and okay, they might make any mistake. Now, did you see where I'm doing? Okay. So for this part, I want to make this, I want to fit this into a
This
next
part,
one.
I believe that part is,
So that part should be like sum over. So this is a series, right? So we can write it like 9 power 0, this is 9 power 1, and 2 squared 2 power 1. So we can write here 2 power 0. Okay. So we can write it like in this way. 9 for I n by 2 power I cube, where I begins from 0 to I equals to 2. How about that? Okay. So if I is 0, it will be like 9 power 0, 2 power 0 and cube. So this is this. If I is 1, then it will be look like this. And if I is 2, then okay. So this looks like a series, and we can rewrite it like this way. 0 to I. So if we want to rewrite this will be like n cube to I, right? So it will be n cube. All right. So we can rewrite this one to 9 power I, 8 power I, and n cube. And since n has no relation to I, we can bring it to the front, right? So the overall expansion will be look like this one. Right? And since 9 by 8 is greater than 1, right? So we may fit this into some formula. Let's see. So we expand this function twice. If we want to expand it up to k times, we will get like this 9 raised to k e n over 2 raised to k plus n cube sum over I equals 0 to, so for 3 this is 2, so this will be like k minus 1 9 by 8 I, right? And if we want to sum this up, it will be look like we want to fit this into the sum formula, and that way it will look like this. So the formula is like this. So this is the ratio. If this, then it will, if R is greater than 1, then it will be R power k minus 1 minus 1. If were less than 1, then it would look like this. Okay, so we are using this formula. What we have till now, will be n over 2 raised to a and 3, and this will be like 1 by 8. So if we bring it front, it will be something like this. Okay. So now every time if we want to the asymptotic value, we will set this term to 1, right? So in that way, if this is 1, then we'll get n equals okay, then k is log n. And if you want to fit these values here, we will get something like 9 log n. So this will be 1 plus 10 cube. This will be 9 log n. This will be 8 log n minus 8 and cube. Right? So we can rewrite this like n log 9. Can you do that? And so this will be like something constant. Say this is 1 or c plus 8 and cube. So we can rewrite this and log 9 and rewrite this and log 8, right? Minus 8. So we'll get n log 9, or we can reduce this, like we want to remove this one, so we can like use this one plus this 8 and cube and log 9. So this is 2 base log, right? So log 8 should be 3, right? So this is basically n cube. So we can do this. So basically 9, sorry, 8 and log 9 and n log 9, so 9 and log 9. So this is order of n. Okay. Got this? Any question? So if you don't, this is no question.
I know it doesn't really matter. Grand scheme, but where'd you pull that 9 in the front from?
Oh, so we have 1 n log 9 and 8 n log 9 here.
Oh,
So
yeah,
1
yeah,
and
yeah, I see.
9.
Yeah.
That's 9. Okay.
Yeah.
And since this is a constant, we can keep
Right,
this
right.
anyway.
So in the test, is there, I mean, I think you said there's not gonna be anything where you have to kind of like write a whole proof down or anything like that, or how is? you know, how
Maybe
they
there are some ways you can like skip some steps here,
Yeah, yeah, okay, okay, all right,
and that will be based on how much you did practice.
all right. Is it, do you know if there's any leniency, like, for like this one, I think I got the steps almost there. I just didn't get to the right answer. I know that's definitely a saying like, or you got it wrong. Is there gonna be any kind of a?
Yeah, there will be some partial marking, I
You
think.
probably have plenty of partial credit on that.
Yeah,
Okay.
so do you want to go to B? Do you have time? Can you do that? So since Dr. Sharma said we have this room reserved up to 5.
Yeah.
So maybe if you guys okay, I can do that.
I want to say I want to skip part B for now and go on with the later ones and try to go over this stuff quickly because we.
Okay, if you have time, we will do B then.
I will erase this, okay? Can I erase it? You all have access to the answer. Is there any question you want to ask about part B? I will try to go over it quickly, but if you want to ask about part B, then I can do that for you. I'll try to go over part B rather quickly and try to get to as many questions as we can today. Okay. Part B, where we have 2 of n equals 2 n divided by 2. So far so good. And then the next n is somewhat weird looking, n over log n. Okay. All right. If you have not noticed, up to this point and probably going forward, whenever we say log of n, that really is just means log base 2 of n. And that's just what we are going to use because well, this is computer science. It's 2 is natural. Okay. So we can expand this. Expand this once, that gives us 2 times 2 over t over n minus 4 plus n of n divided by 2 and then divided by log of that. So 2 of log by 2. And then I will put on this part. We're good, right? Okay. And simplify a little bit, that gives us 4t of n divided by 4 plus here's a 2, and then here's this 2 and this 2 cancels out. So that becomes n divided by log of n divided by 2 plus n divided by log n. Okay, Now, we could like do this further, but I want to point out something here. In the, it doesn't, the answer skips this part, right? We can do, since we have log base 2 right here, then we have log minus divided by 2. Really, it's just equal to log of n, this one, minus 1. Right? Simple logarithmic algebra. Now, with this thing in mind, the next step is going to be much easier. So that becomes a times q of over 8 plus n divided by log n plus n divided by log n over 2, which at this point equals all right, and that equals the plus log minus 4, which equals n over n minus 2. So, all right, I used too much space. I'm gonna save the space. This equation in mind, we can do this k times that comes to the power of k times t of divided by 2 of k plus we get this n's out of it. Of this n's, we can get it out. So n times 1 over n plus 1 over log n minus 1 plus 1 over log minus 2 plus so forth plus 1 over log n minus k plus 1. That's the expression. Okay. And we let k equals log n. The network, this is the value that we select for k to b that will bottom out the recursion. And this becomes it is log n equals n times 1, which is constant. Oh, which is n. And then plus n times. Now that's an interesting part. 1 plus 1 over 2 plus 1 over 3 plus so on and so forth plus 1 over log n. Are we good with this? This one. This one really is just this with the order reversed. Since it's just calculating the sum of the series, when you reverse the order, it becomes the same. Right? Because if k is log n minus log n plus 1, that's just 1. And you have seen this, right? This is called the harmonic series, which say 1, 2, 1 plus 1 over 2 plus 1 over 3 plus 1 over n is O of log n. This one, you should probably go over this in class, right? This is the growth of harmonic series, right? it goes to logarithm. And here we replace this, since we are adding only up to log n. Here, this becomes log n. And this should become just log. Okay. And all right, this times this. So the final answer for this question is n log n. Are we good with this part B? Any questions you want to ask before I move on to the next one? Questions? All good? Okay, let's move on to part E. All right. Part E, I don't know what to feel about this. It says that the answer sheet says that part E can be solved using substitution. I'm not sure if it's called substitution or it's called just randomly guess something and then gets the shear log of it because you guess it right in one try. So let's go over this. I got to say I kind of don't like part E because part E does not. I don't know what it's intended to test you.
Yeah, when I solved it, I had gotten something where it fit within this bound, but it wasn't the tightest bound because I had chosen correctly. I should have probably just ran it through one more time in something tighter and then.
Yeah, okay. So part E, we have T of n expands to.
And then it works.
Yeah.
Exactly.
Four plus n. All right, since there is an n right here, we know it's at least linear.
Mhm.
So it's omega n. Now, the thing is this so this is a lower bound. Now, the question is this an upper bound? Is this a lower of n? Try it. But the way you try, if you look at the proof, you can probably recognize this as this is a mathematical induction. I'm sure everyone here should know about mathematical induction here, where we suppose, in fact, this is strong induction. Strong induction is slightly different, but still induction. Okay. Assume, okay. Assume that there exists some C such that Dn is smaller than C of C times n. Now, for all, we should try this to see. Looks like I'm taking so much time. My apologies, but all A in 2 n minus 1. And how about bit 4 is we have Tn is so still the same stuff. T over 3 plus 2 T over 4 plus n, which is smaller than or equal to this one is C over 3 n plus 2 times 2C times n over 4 plus n, which equals 5/6 C N C this plus N, which equals 6C plus 1 times N, which and so the inequality holds for all C greater than or equal to 6. And that's the proof. That's the proof that this thing is linear. It's so open. Any questions for this part? All good?
I mean, yeah. So kind of what I did, I kind of did the same thing, all the same steps, but I guessed and log n.
Mhm.
And obviously, like I still got it, that it
Yeah.
still holds.
Yeah.
On the test, I assume we'll get like partial credit,
Mhm.
like most of the way, or
Yeah.
something like that.
Probably yes, right? We have to confirm with the professor
Right.
about how to grade this.
So last to last time I was his TA, and the test he grade all the test by himself. And for some questions I saw that he was like binary, like maybe that's for the algorithm design. For this part I'm not exactly sure, but there is a possibility we'll get some partial credit. But for the algorithm design, I saw that he was kind of binary, either full credit or no. But people got full credit for some kind of solution if the solution was aligned to the real solution, not something that that.
Okay, can we erase this and move on? And so we don't have too much time, so let me try to squeeze this out. Question number 3. Are we all good with question number 3? Oh, thank you. All right, let me just go over question number 3 real quick. Okay. X equals x plus 1. That's the actual operation that is performed by this algorithm. This thing takes constant time, okay? Good. All right. And so for x, let's say for I equals 1. For I equals 1. N times. This happens n times, okay? For I equals 2, n divided by 2 times. Are we good? Because for the j is from 1 to n. J every time is updated by the value of I, right? So this time is n divided by 2 times. I is 3, and over 3 times. 4 over 4 times. So this all becomes n plus n over 2 plus n over 3 plus 1. Oh, wait. Yeah, right. N over n, which is 1. And this is the that is just n times 1 plus 1 over 2 plus 1 over 3 plus. We just see this before. This is the harmonic series, right? So this is log n. And here we have n. So the total is O of n log n. Are we good? Okay. Now, the slightly tiny little bit of detail is that x here, it actually records exactly how many times this operation is performed, because in the beginning x is 0. And when we are looking at here, we have to like do this for, right? We need to do for and everything. But you probably have, I don't know if the professor has mentioned this before, but in analyzing the algorithms, most of the time, let's say more than 95% of the time, maybe 99% of the time, you can ignore the floors and ceilings, and it's going to be just fine. The asymptotic behavior is the same, even if you just forget about the floors and ceilings and everything. Okay. All right, that's question number 3. Good. Oh, good. Let's try question number 4. Number 4 is merge sort. Now, suppose instead of dividing so 4, merge sort. So instead of dividing merge sort by the list into 2 parts, you now do it into 3 parts and merge them together. And the thing that becomes it is just T of n equals 3 times T of n over 3 plus say plus O of n. Now, this part is the merge part. Okay. This is the merge part, and this is the recursion. I hope I don't have to go over this again, but it really is just log n. So it should come with no surprise that the asymptotic behavior states is still in log n. Okay. And merge the 3 sorted parts together. Well, you can merge the 3 sorted parts together with exactly the same way as you merge the 2 parts, 2-part variant. Okay. So, should I go over more of this question, or are we good? Like, really, the most part is just this one. Like, if you know this equals n log n, you're good.
This won't really make much of a difference, but in this case, since you're dividing it into 3,
Yes.
3 times, it's a base of 3 in this case, correct? Or
Log 3 n. I think so. I don't know. I could be wrong. But remember that when we look at logs, again, this is logarithmic algebra. The base, more often than not, you can ignore the base, because remember, like we have something like log base b of a, really is just log c a divided by log c b, where c can be anything that's like bigger than 2 or something. So if we have something like log 3 of n is c times log 2n, where c is some constant that yeah, you can go over this by yourself, but this is the general case for all the logarithmics. Okay, can we Are we good with question number 4?
We pretty much to answer that question, it doesn't make much of a difference if we divide it 3 times.
Yes,
or-
yes. Yes. And in terms of merging them together, the merged part is, I would say, actually the same. Merge them by merge 2 sorted lists and merge 3 sorted lists. If the total number of elements are the same, then I would say that the overall running time should be the same. Maybe off by a little bit of overhead, but so even the hidden constant inside big O, if I'm right about it, it should not change. Question number 5. Question number 5 is something that I want to talk about a little bit more. Part A, we have a sorted list. And part A, we have a sorted list. One of them is missing. And what's nice about it is that it's guaranteed that the elements in the sorted list are consecutive integers starting at 0. So we can do something like this. And then just an example, right? Like suppose this is the number of like this, and then say one of them is missing. Now the only thing you're allowed to ask is what is the J speed of the A of I, where the indices are 1, 4, 5, 6, 7. Yep. Okay, good. All right. So there are 2 ways of doing this. Both of them are, I would say both of them are, in the end, they are all binary searches. So if we are looking at a complete list without a missing number, then this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, right? And then for the first solution here, have you focus on the least significant bit, where it denotes whether the number is odd or even. So the least significant bit here is 0. So okay, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, something like that. Now suppose one of them is missing. Say 1 is missing. Okay. Now what should happen? What should happen if 1 wasn't still there? Then okay, let me try this. Oops, I just wrote the same thing 2 times. Absolutely not necessary, but whatever. This is the indices, and this is the number. The first one, have your that. So for all the indices, the number should be even, and for all the even indices, the number should be odd. So this is in the case where one number is missing. So if no number is missing, then odd index even number. And even here. Spot. Good. Okay. Now if one of them is missing, this will change all the indices as well. That becomes 2, 3, 4, 5, 6, 7. If one of them is missing, then all the indices that are after that one will violate this rule, where all the index gives an odd number, and even index gives an even number. So this is enough to do a binary search. So you can do something like first you check this number 3. What is the least significant bit of index 3? Says it's 1, which means that the missing number is before that. Okay, and the next one you can say is like, what's the next number here? Check the least significant bit of number 1, and it's 0. So the missing number is after 1. So it's before 3, and it's after 1. And then you can probably do another check on 2 or something, and then it's 0. Then you can know exactly what number is missing right here. So that's the first solution. The second solution is slightly more complicated, but has more potential use for later problems. Which, instead of concerning the least significant bit, where it concerns the even and oddness, it concerns the most significant bit. Okay, let's try this. The most significant bit, you can see that we have this. These are zeros. These are all zeros, and they are ones. Does it say that the okay? The problem doesn't really say that the total number of elements is like a power of 2 minus 1, but we can probably assume that. But so let's say this is the power of 2 minus 1. So we have 3 bits for this binary representations. So the point of the second approach is to look at the middle one of the list, and see if it has the most significant bit and the least significant bit. Okay. So what that means is, again, let's look at another version where if no number is missing, where we have 1, 0, 1. In that case, we can do check the most significant bit of, say, so A divided by 2 is 4, index number 4. If no numbers are missing, then the most significant bit for index number 4, it should be 0, because that is the first half of the list, where all the most significant bit here are 0. And then the second half will have the most significant bit here as 1. Okay. If the number missing is before it, then the fourth index will have a most significant bit of 1. And if you can see that, you know that the missing number is in the first half of the list. Or if the number that's missing is in the back, then given the fourth number, the fourth one will have a most significant bit of 0. So the thing is that when you are looking at the middle of the list, if the most significant bit is 0, it means that no number in the first half is missing, and the missing one has to be in the second half. If it's 1, if it's in this case where it's 1, then it means that the missing number is in the first half of the list. I don't know if I get that part clear. Okay. Now, once we know which part of the list contains the missing number, then we can do the same again, this time looking at the second significant bit. Okay. Number 2 here, the index number 2 here has the second significant bit of 1, which means that the missing number is before it. And then the next step is, of course, to look at index number 1, where the second significant bit is 0. So the number that's missing is 4. So that's 0, 0, 1. I don't know if I made that clear, but like this is another form of binary search, where every time you look at the most significant number bit to determine which half of the list the missing number is, and then use the second one to go over like which quarter of the list. And if it's longer list, then use the third significant bit to look at which octet it is, or something, so on and so forth. So this is also binary search. Okay, this concludes question 5, part A. All right, can we move on to part B now? Part B, we have unsorted list. And we are required to, oh, and by the way, for the runtime for part A, since both are perfectly binary search, they are just log O of big O of log n. Okay. All right. And part B, we have unsorted list. Unsorted list, we are to find that. So given a list of numbers, all right, we can use an approach that's similar to solution 2 of part A, where we first ask the most significant bit of every single number right there. There are n numbers, and I would say, like, for the sake of simplification, we can assume that n is to the k minus 1, the number k. That way, every number here can be represented using the bit length of k. We don't have much time really. So the thing is to ask most significant bit of everyone, every element. And if no number is missing, they should have the same number of zeros and ones. right? But since one is missing, one of them, so the most significant bit, 0 and 1, one of them should have one more element than the other. And that will, and the one with less, so let's say there are like 32 numbers with most significant bit of 1, and 31 of them are 0, which means that missing numbers most significant bit is 0. Okay? All right. So we have asked n times so far. The next step is to look at all of the numbers with the most significant bit of 0, right? And then ask all of them the second significant bit. Good. So the next step is ask second significant bit of all that with say 0 most significant bit. All right. And using the exact same reasoning as above, we get to know exactly the second most significant bit of the missing number. And now we have done it n divided by 2 times. Okay, and so on and so forth. N divided by 4, n divided by 8, up until 1. Okay, so using this method, we can determine the entirety of the missing number, all the bits of the missing number using how many times? N plus n divided by 2 plus n divided by 4 plus, you should know this, right? It equals to n minus 1. And so that is linear. Are we good? All right, so we have question number 6 and 7 left, and 3 minutes. What do we want to do with this?
Maybe we can look over them, and the next time we can come back with questions.
Sure,
We
sure.
do that for
Sure.
10, 15 minutes,
Sure.
maybe, and then we can do homework too.
When's the next time for this?
Next week?
Tentatively, it should be next Tuesday. Yeah. Because I believe the professor has said in class that next Tuesday is next Wednesday is your exam, right? And he intended to